Welcome to This Explainer. I am absolutely thrilled to guide you through this topic today. We're going on a macro to micro journey into one of the most phenomenal pieces of engineering on the planet, the human kidney. We're going to visualize exactly how this biological machine operates step by step, mapping out the entire mechanism of urine formation. All right, let's just jump right into a totally staggering stat. Did you know your kidneys filter about 180 liters of blood every single day? That is an absolutely massive volume. Picture roughly 92-liter soda bottles just lined up. That's your blood being filtered, day in and day out. But here's the crazy part. Out of all those 180 liters, your body only actually produces about 1 to 2 liters of urine. So it really begs the question, right? How does this incredible filtration system actually work to keep you healthy? Figuring out these mechanics isn't just about marveling at biology. If you're a student, nailing this down is absolutely crucial for acing your O-level biology exams, especially in the homeostasis and excretion sections. Plus, getting a grip on this exact mechanism is the foundation for understanding real-world medical applications, like how dialysis machines literally save lives. Here is our roadmap. First, we'll cover the anatomy of the kidney. Then, ultrafiltration under pressure, the selective reabsorption process, and finally, common exam mistakes.
Let's start with Section 1, Anatomy of the Kidney, moving from macro to micro.
Let's take a look at a cross-section. Notice this outermost layer, Region A, the renal cortex. Think of this as the outer shell of our biological filter. Visualizing exactly where this sits physically is step one to understanding how fluids actually flow through the whole organ.
Now moving inward, we hit this really distinct middle section. This is Region B, the renal medulla. It sits directly beneath the cortex and acts as this critical transition zone for all the fluid that's being processed.
Following the downward flow, we reach Region C, the renal pelvis. You can think of this area like a giant anatomical funnel. This is the collection zone where the newly formed final urine actually starts its journey right out of the kidney entirely.
Now let's zoom all the way in dynamically to the microscopic level. See this tiny tubule labeled D? That is the nephron. Your kidney isn't just one giant filter. It's actually made up of literally millions of these tiny functional filtering units. The nephron is where the real magic of urine formation happens, and it does this through two main processes.
Which brings us to Section 2, ultrafiltration under pressure, specifically looking at the glomerulus at work.
Check out the immense physical force at play here. Blood enters the glomerulus, which is a capillary network inside the nephron, under incredibly high pressure. This specific mechanical force is exactly what pushes fluid out of the blood and into the Bowman's capsule to form what we call a filtrate. Without this high blood pressure driving it, this critical filtration force just wouldn't exist.
So what actually makes it through this high-pressure filter? If you look at the left, pushed into the Bowman's capsule, we've got water, glucose, salts, and urea. This becomes the filtrate. But check out the right side. Larger molecules, things like proteins and red blood cells, they're physically just too big to pass through, so they stay safely inside the bloodstream. It's a remarkably precise physical sorting mechanism.
Moving right along to Section 3, selective reabsorption, where the body reclaims the essentials.
Okay, so we have this massive volume of initial filtrate. Moving to step 2, tubule selective reabsorption. As that filtrate flows through the microscopic tubules of the nephron, the body essentially realizes, hey, I can't afford to lose all this water and nutrition, so it starts pulling them back into the bloodstream.
During this sorting phase, essential substances like glucose, vital ions, and water are reabsorbed back into the blood. The body absolutely needs to save these. Meanwhile, the waste products, things like urea and excess salts, just continue their journey through the tubules to ultimately be excreted as urine. It is just a brilliantly efficient reclamation system.
Now, let's pivot to Section 4, Common Exam Mistakes. I definitely don't want you losing vital marks here.
A huge myth we see all the time is that ultrafiltration is a purely passive process, kind of like pouring water through a coffee filter. The reality you absolutely must remember is that it is strictly driven by high blood pressure. If an exam question asks what drives the formation of the filtrate in the glomerulus, don't just say filtration. You have to explicitly state that the high pressure of the blood is the driving force. That's a total game changer for your grade.
Let's look at another common pitfall. The myth here is complete reabsorption, this idea that the body absorbs everything back into the bloodstream. The reality is that this process is highly selective. The nephron's tubules are perfectly engineered to reabsorb only the specific amounts of water, glucose, and ions your body currently needs to maintain homeostasis, explicitly leaving the waste behind. So remember, highly selective, not complete.
Finally, Section 5, Final Recap and Action, Mastering the Nephron.
All right, here are the 3 non-negotiable takeaways you need to pull from this explainer. 1. Nephrons are the millions of microscopic filtration units inside the kidney. 2. The glomerulus is where high-pressure ultrafiltration occurs, pushing out the initial filtrate. And 3. The tubules are where highly selective reabsorption happens, returning vital substances back to your blood and leaving only waste to become urine.
And here's my ultimate, highly focused tip for the students watching. Don't just watch these diagrams, recreate them. Practice physically drawing and labeling the gross anatomy of the kidney and the microanatomy of the nephron. Drawing those directional arrows and writing out the variables yourself is scientifically proven to guarantee recall when you're sitting in that exam room.
To wrap things up, I want to leave you with a real-world engineering question to chew on. We know medical science uses dialysis machines to save the lives of people whose kidneys fail. But if a machine is replicating this brilliant biological system, how exactly do you think medical engineers mimic the microscopic, high-pressure selectivity of the glomerulus using artificial tubing? It's a fascinating thought that connects the biology we just learned right to the cutting edge of health tech. Thanks so much for joining me on this explainer, and keep questioning how the amazing machinery inside you works.